Welcome to our exploration of Object-Oriented Programming, OOP, in Java. OOP is a paradigm that organizes software design around data, or objects, and the methods that operate on these objects, rather than focusing solely on logic and procedures. This approach is significant in modern programming as it allows for greater flexibility, making it easier to manage complex systems and keep code organized. In the realm of Java, a language known for its robustness and versatility, OOP is a fundamental aspect. It supports key features of OOP either natively or through libraries, providing the building blocks for creating a wide range of applications. From creating interactive web applications to complex gaming engines, understanding OOP is paramount to mastering Java and unlocking its full potential. Now that we have a basic understanding of OOP, let's delve into its key concepts, starting with encapsulation. Encapsulation is one of the fundamental concepts of OOP. What do we mean by this? Well, encapsulation refers to the bundling of data, along with the methods that operate on that data, into a single unit called a class. A class, in essence, is a blueprint for creating objects in Java. In the realm of Java, to demonstrate encapsulation, we create classes. Let's consider a practical example. Imagine we're building a simple banking application. We might create a class called account. This class will define attributes such as account number, balance, and account holder. Now these attributes are the data we're trying to encapsulate. But encapsulation isn't just about data, it's also about the methods that act on this data. So within our account class, we might define methods like deposit, withdraw, and check balance. These methods are designed to manipulate the data attributes in some way. For instance, the deposit method could increase the balance, while the withdraw method decreases it. The check balance method, on the other hand, might simply return the current balance. Each of these methods encapsulates a specific operation that can be performed on an account. And that's the beauty of encapsulation. It allows us to bundle related data and operations together into a neat, self-contained package. This makes our code easier to understand, maintain, and debug. But it's not just about bundling data and methods. Encapsulation also provides control over the data. By making the attributes private, we can ensure that they can't be directly accessed or modified from outside the class. Instead, they can only be manipulated through the methods we've defined. This gives us a way to enforce rules and constraints on how the data is used. For instance, we could ensure that the balance can't go below 0 by adding a check in the withdraw method, or we might restrict the account number to a certain format. By doing so, we're adding an extra layer of security and robustness to our code. With encapsulation, we can create well-defined objects, but how do we hide certain details? Let's find out in the next section. Data abstraction and information hiding ensure that we expose only what's necessary. These two principles are like the secret agents of object-oriented programming, working behind the scenes to keep your code secure, elegant, and efficient. Let's start with data abstraction. This is all about simplifying complex systems by breaking them down into manageable, bite-sized chunks. Imagine you're crafting a digital symphony. You don't need to know how every single note is produced by the computer, right? You just need to know that when you press a certain key, a certain sound is produced. That's data abstraction in action. It lets you focus on the big picture without getting bogged down in the nitty-gritty details. But abstraction doesn't just make your life easier, it also keeps your code safe. That's where information hiding comes in. By tucking away the inner workings of your objects, you protect them from unwanted interference. It's like putting a do not disturb sign on your object's door. Now how do we achieve this in Java? Through access modifiers, public, private, and protected. These are like the bouncers of your code, deciding who gets to party with your data and who gets left out in the cold. Public means anyone can access the data. It's an open house. Private, on the other hand, is much more exclusive. Only methods within the same class can access private data. And then there's protected, a middle ground that allows access to classes within the same package and subclasses. Let's consider a bank account. You wouldn't want just anyone to access your balance, right? So you'd make that data private. But you might want to allow certain trusted methods like deposit or withdrawal to interact with your balance. That's the beauty of data abstraction and information hiding. They help you maintain a clear, secure structure in your code, allowing you to build complex systems without losing yourself in the details. Abstraction and hiding are essential, but how can we make objects behave differently? This leads us to polymorphism. Scene script. Polymorphism is what gives OOP its versatility. Polymorphism is a Greek word where poly means many and morphos stands for forms. In the realm of Java and object-oriented programming, polymorphism serves as a mechanism that allows actions to behave differently based on the object performing them. This is the beauty of polymorphism. It allows us to design a method once and then have it behave differently for different object types that use it. Imagine you're a chef in a kitchen. You have a set of instructions or a recipe. But depending on the ingredients you use, you could end up with a cake, a pizza, or a salad. That's polymorphism in action. The same process can yield different results, based on the object, or in this case, the ingredients. In Java, we achieve polymorphism in three main ways: method overloading, method overriding, and through the use of interfaces and abstract classes. Firstly, method overloading occurs when we have multiple methods with the same name, but different parameters within a single class. It's like having different recipes for the same dish, each with a unique combination of ingredients. Secondly, method overriding is when a subclass provides a specific implementation of a method that is already present in its parent class. It's like tweaking a recipe to suit your taste. Lastly, interfaces and abstract classes allow us to define methods that must be created within any class that implements them. It's like a recipe that must be followed, but leaves room for personal touch. Let's consider a real-world Java example. Suppose we have a superclass called Animal, with a method called Sound. In the subclasses Dog and Cat, we override the Sound method to return Bark and Meow respectively. When we call the Sound method on an object of type Dog or Cat, the appropriate sound is produced. That's polymorphism. Polymorphism adds flexibility, but how can we reuse and organize our code better? Enter inheritance. Inheritance allows us to create a hierarchy of classes for better organization and reusability. This statement encapsulates the power of inheritance in object-oriented programming. But what exactly is inheritance? Inheritance is a principle of OOP that allows us to define a new class based on an existing class. This existing class, often referred to as the parent or base class, passes its attributes and methods to the new class, which we call the child or subclass. This mechanism allows us to reuse code, reduce complexity, and organize related classes in a hierarchical manner. So, how do we implement inheritance in Java? It's pretty straightforward. We use the extends keyword. The extends keyword signifies that the new class is a subtype of the existing class. Imagine you're creating a program for a zoo. You might have a parent class, Animal, with attributes like name and age, and methods like eat and sleep. Now if you want to create a lion class, instead of defining all these attributes and methods again, you can just make lion a subclass of animal. This means lion automatically inherits all the attributes and methods of animal. There's more. With inheritance, you can also add or override methods in the child class to provide specialized behavior. For instance, the lion class can have a unique method called roar, or override the eat method to specify that lions eat meat. Now it's important to remember that Java supports single inheritance, meaning a child class can have only one parent class. But don't worry, through interfaces, Java provides a way to achieve something similar to multiple inheritance. Inheritance is a powerful tool in your OOP toolkit. It promotes code reusability and hierarchical organization of classes. However, it's just one piece of the puzzle. Inheritance, along with the other concepts, forms the backbone of OOP. Let's recap. And there we have it. Inheritance demystified, and its implementation in Java explained. We've covered a lot of ground today, but remember, practice makes perfect. Keep coding, keep exploring, and see you next time. We've covered a lot of ground today, exploring the key concepts of OOP in Java. We kicked off with a brief overview of object-oriented programming, highlighting its significance in modern programming. Then, we delved into the idea of encapsulation, demonstrating how Java bundles data and methods within a class. We discussed the role of data abstraction in hiding implementation details, and how Java uses access modifiers to achieve this. We also explored polymorphism, showcasing its ability to allow objects of different types to respond differently to the same method call. Lastly, we touched on inheritance, illustrating its role in creating a hierarchy of classes for code reuse and polymorphism. Mastering these OOP principles in Java offers numerous benefits. It leads to better code organization, reusability, and flexibility, all of which are vital in the ever-evolving field of programming. With a firm grasp of these concepts, you're well on your way to becoming a proficient Java programmer. Keep practicing, and happy coding.